Okay, so our next topic is we want to start talking about the explicit representations, and I want to talk about the finite dimensional irreducible representations of SU2. And those of you who have done quantum mechanics, you know this. You know how this is done. But what you don't know is that this forms a backbone for the representation theory of all the Lie algebras. So it's worth reviewing it again. Okay. So we start with the SU2 Lie algebra. So it's let me write this with J using notation from quantum mechanics, angular momentum. Okay, so you guys know this, right? So explicitly, there are three non-trivial equations here. J1, J2 is I, J3. J2 commutator J3 is I, J2. And then J3, J1 is I. Sorry, this should be 1, right? 2, 3, 1, yes. Should be J, I, 2. And all the other ones, of course, are 0. Now, let's introduce a different basis. Let's introduce a non-Hermitian basis. Inspired by the harmonic oscillator. And let's define J plus minus to be J1 plus minus I, J2. So then we have that J plus minus are not Hermitian, right? So if I take J plus, take its Hermitian conjugate, I get J minus. And if I take J minus, take its Hermitian conjugate, I get J plus. Now, if we express these three commutation relationship in terms of, J plus, J minus, and J3, then we get something like this. The commutator of J3 and J plus is plus J plus, and the commutator of J3 with J minus is minus J minus. And so there are two commutators here, two commutation relationship, and then we also have what is J plus and J minus. J plus and J minus is 2J3. Okay? Now, can someone remind me what the rank of SU2 is? Do you remember what the rank is? You guys haven't prepared for the quiz, I see.
Isn't it the same as the dimension of the algebra or something?
No, it's a dimension of a subalgebra. What kind of subalgebra is that?
Is it the dimension of...
Is it 1?
Sorry? What was it you said? Somebody said something.
I said, is it 1?
Yes,
I
it
said
is 1.
1.
Why is it 1?
Sorry.
Why is it 1?
Because it makes one pair.
One pair of what?
I know what it is. Rotation.
Right. I see what you're saying. Yeah. So you have retained the intuition. Yes, that's good. Yeah, that's correct. So who was that, by the way?
Fiza.
Yeah. So what Fiza is trying to say is that in 3 dimensions, we have 1, 2, 2, 3, 3, 1, 3 planes, right? So if I rotate in one plane, there is no other rotation that is independent of that rotation, right? So that means that of these 3 rotations, we can choose only one rotation to be part of the Curtin subalgebra. Remember, the Curtin subalgebra is the algebra of the maximal number of mutually commuting generators. So if you were in 4 dimensions, then we would have 1, 2, 2, 3, 3, 4, 4, 1. These would be the planes of rotation. And then we could choose, say, 2, 3, and 4, 1 to be rotations which commute with each other. In that case, the Curtin subalgebra, the dimension would be 2. Right. But since SU3 is essentially morally equivalent to SO3, there is the Curtin subalgebra can have only one element. And the dimension of the Curtin subalgebra is what we call rank. And that is 1. Okay? So yeah, good, Fiza. So there is only one element of our Curtin subalgebra, and we can choose any guy. We choose J3 to be the Curtin subalgebra, okay? And this is kind of a, this is a, this is like an arbitrary choice. This is a conventional choice. By the way, if you are dealing with a group SUN, then the dimension of the Curtin subalgebra is just n-1. So for SU3, you will see that the Curtin subalgebra for SU3, the Curtin subalgebra will consist of lambda 3 and lambda 8, the traditional choices. Okay, so for this guy, we are choosing the Curtin subalgebra to be J3. Okay, so the rank of SU2 is 1. So I won't be able to finish everything today, but let me just, before leaving, tell you about the Casimir invariant. So there is an operator which we call J squared. It is J1 squared plus J2 squared plus J3 squared. So it's a nonlinear combination of generators, right? It's a nonlinear. Now, you can show by using the, algebra that we know that this commutes with all the i's, right? So this is at the Lie algebra level, right? Of course, if this operator commutes with all the generators, what will happen if I calculate this, where G are the group elements, that is, has this form. What will this be?
Should also be 0, I guess.
Exactly, for all G in SU2. So what does it say about the form of J squared? According to Schur's lemma, what do we know about J squared?
Oh, is it an irreducible representation?
No, we are building irreducible representation of SU2. That is suppose we have those matrices, those J matrices. In that space of matrix, what would J square be?
Oh, it would be a multiple of the identity.
Exactly. So according to Schur's lemma,
I have an emergency. Can I leave the meeting now?
yes, of course, yes. Well, who was that?
Zabir, sir.
Okay, sure. Thank you, Zabir.
Thank you, sir. Have a good day.
No worries. So according to Schur's lemma, J squared is some constant times the identity, right? And J squared is called the Casimir invariant.